Hello, my name is Paul Myers, and I am a student in the Electrical Engineering and Computer Science Department here at the University of Michigan. Today I would like to discuss with you the design of ultra-low power CMOS circuits for cubic millimeter scale sensor nodes. This project was sponsored by the 2014 SURE program and was directed by Professor David Blaauw. So our discussion today will proceed as follows. First, we will introduce the cubic millimeter sensing system for which we will be designing the low power circuitry. Then, we will discuss the motivation for the research conducting during this past summer. Next, we will provide an example of a low power circuit, namely a compact voltage reference. And finally, we will show preliminary simulation results and the silicon layout of the test chip submitted for fabrication before concluding with the acknowledgments. So let's begin by introducing the cubic millimeter sensing platform. Advancements in computing technology have progressed at an astounding pace. In the 1940s and 1950s, the first computers were designed primarily to calculate ballistic trajectories for the United States military. These computers were referred to as mainframes and were large enough to fill a spacious room. An example of an early computer, the ENIAC 1, is shown here. In 1973, Ted Hoff of Intel Corporation produced an important advancement in computing technology by introducing the first microprocessor, the Intel 4004. The development of the microprocessor provided the impetus for the invention of inexpensive compact electronic devices, such as the personal computer. Later inventions include the laptop and, today, the smartphone. While devices such as smartphones integrate highly complex functions into a single device of small form factor, the versatility of these devices is largely hampered by high power consumption. Near the turn of the millennium, a group at the University of California at Berkeley invented the first practical smart dust mote, capable of integrating sophisticated sensing devices into a single design of cubic millimeter volume. This design has influenced a number of research groups across the world to develop sensing platforms of even smaller scale and higher efficiency. In particular, the University of Michigan has made an important contribution to this development by introducing a sensing platform of unprecedented capability. So let's introduce this sensing platform. Shown here is the Michigan micromote, commonly referred to as M-cubed, in its most current form. The design consists of 5 layers, each of which executes a specific function in the overall system. Development of the device has spanned much of the latter half of the previous decade and has involved the work of dozens of students from nearly all parts of the world. So let's briefly consider each of the layers in the M-cubed system. The first layer, shown in green, provides a number of functions, including energy harvesting by way of a solar cell and image sensing circuitry. This layer is fabricated in 130 nanometer process technology. The second layer, shown in blue, is reserved for the battery. The battery, which is a thin film solid-state device, is required to provide the entire system with a stable source of power over the lifetime of the system, which could be as long as a decade. The solar cell in the first layer is used to recharge the battery. The third layer, shown in pink, is fabricated in 65 nanometer technology and provides such functions as digital signal processing and memory. The fourth layer, shown in orange, is fabricated in 180 nanometer technology. This layer provides such essential functions as power management, brownout detection for the battery power supply, and global system communication using light. The final layer, shown in brown, is the decapacitance layer, which is used to suppress undesirable fluctuations in the power supply. Such a highly complex system requires careful design, particularly at the circuit level. A notable challenge of designing a wireless system is managing the power supply. We therefore consider next the basic design of the circuitry for this purpose. Suppose we have a circuit, which may be assumed to contain a wide variety of component types and integrate a range of functions. And let's further assume that some of these functions contain, in particular, sensitive analog circuitry, the proper functioning of which is contingent upon a stable power supply. Although we would like to assume that the power supply is stable, if the system is powered by a battery, the supplied voltage may vary dramatically across various operating conditions. Shown on this plot is the battery voltage as a function of the lifetime of the battery. As we can see, the battery voltage is not at all stable across the lifetime of the battery. Note the prominent fluctuations in the output voltage. These fluctuations may be attributed to such factors as variations in the ambient temperature, which may occur upon transition from day to night. If a wireless sensing platform is to operate reliably in all manner of locations, then a mechanism for stabilizing the output voltage must be included in the system. So let's consider a mechanism for regulating the voltage seen by the circuit we considered earlier. Suppose we have a battery whose output is used to power the system. To determine if the output voltage varies enough to jeopardize the proper functioning of the circuit, a simple regulation scheme may be employed. A standard approach is to use a component called a comparator. A comparator examines the voltages at its input terminals and outputs a signal based on the relative values of these voltages. This signal may then be passed to a block of processing circuitry. If we are to monitor the battery voltage, we need a suitable reference. This reference is called a voltage reference. So let's now consider the criteria that may be used to design a voltage reference. In designing a voltage reference, we will consider the following metrics: power consumption, temperature stability, supply variation rejection, and process variation tolerance. Let's consider first power consumption. A transistor may be compared with a faucet. When the transistor is on, the device will draw a certain amount of current, depending upon the magnitude of the applied voltage. When the device is turned off, the transistor will produce a small but non-zero current, much as a faucet in a kitchen sink leaks when it is supposed to be off. Conventional voltage references often utilize active transistors, and these references persistently consume large amounts of power. We therefore consider the design of a voltage reference that uses an off-state transistor to drastically reduce the power consumption of the design. Shown here are two ultra-compact, ultra-low power voltage references. These circuits consist of two transistors each. The upper transistor, which is an NMOS device, is off, which limits the current drawn by the circuit to very small values. According to the published literature, this design is capable of consuming approximately 3 orders of magnitudes, that's 1,000 times, less power than the next lowest power design. The lower transistor is connected in a manner called the diode connection. The lower device may be either an NMOS device or a PMOS device. Choosing a PMOS device has been shown to offer improved temperature stability. So with that, let's now consider the temperature stability in more detail. Voltage references are generally subject to 2 types of temperature dependencies. The first type of dependence is called proportional to absolute temperature, or PTAT. For PTAT dependence, the output voltage increases as the temperature increases. The second type of dependence is called complementary to absolute temperature, or CTAT. For CTAT dependence, the output voltage decreases as the temperature increases. Now, for some designs, having a CTAT or a PTAT dependence is desirable. But for our case, we would like a more consistent output voltage. So for a well-designed voltage reference, the output voltage will remain constant as the temperature is varied. So let's consider the factors that will allow us to achieve such a balanced output voltage. For the 2T reference, the output voltage is related to the natural logarithm of the ratio of the device widths. By properly choosing the ratio of the device widths, the temperature dependence of the reference may be eliminated. The temperature sensitivity is defined by a quantity called the temperature coefficient. So shown on this plot is the temperature coefficient plotted as a function of the device ratios, and we can see a clear minimum point that may be achieved by selecting the proper ratio. So let's now consider the power supply rejection requirement. Simple analysis will show that the output voltage of the 2T reference is given by the equation shown here. These end terms are referred to as the subthreshold slope factors. These terms are the transistor threshold voltages. This symbol denotes the thermal voltage. These symbols refer to the carrier mobilities, and these parameters are the oxide capacitances. Finally, the transistor lengths and widths also affect the output voltage. Insensitivity to supply variation is implicit in this equation, as none of the terms, to a very good approximation, depends on the supply voltage, denoted by the symbol VDD. So therefore, we can see that this voltage reference design provides sort of an innate insensitivity to the supply variation. Finally, let's now consider process variation tolerance. Let's again consider the voltage reference output equation. The output voltage depends on the difference of the threshold voltages, rather than on the absolute values of these parameters. Thus, if the threshold voltages vary, the relative change in each voltage should approximately match that of the other voltage, thereby reducing the effect of threshold voltage variation. We can ensure that this tracking occurs if the layout for these devices is done very carefully. Moreover, the mobilities, capacitances, and device dimensions appear in the natural logarithm term, which suppresses variations in these parameters. The circuit, therefore, exhibits an innate tolerance to this process variation. So now let's show some preliminary simulation results. The figure at left shows the output voltage of the reference as the function of the ambient temperature for 3 different supply voltages. These plots were obtained for circuits with optimized device sizes. Across supply voltage, the variation is less than 1%. And likewise, across temperature, the variation is also less than 1%. At right, the output voltage is plotted as a function of the supply voltage for 3 different temperatures. Again, we see that the variation of the output with supply voltage is less than 1%. And the variation again with temperature is also less than 1%. So we fabricated these devices on a test chip in a commercially available 180 nanometer process technology. And so shown here is the silicon layout as designed using industry standard CAD tools. The chip measures 1.3 millimeters length and 0.6 millimeters in width. This test chip was submitted for fabrication and is expected to return in late August 2014 for testing. We intend to measure the output voltage across a range of supply voltages and temperature values, and perform a statistical analysis of the die-to-die variation and yield caused by process variations. So, in conclusion, I would like to sincerely thank the following people and groups for their support during this project: Professor David Blaauw, Professor Dennis Sylvester, Dr. Jiyoung Fu, In-hee Lee, the students in the DD Lab, Mr. Tony Wong, the staff of the SURE program and the ISD department, the Department of Electrical Engineering and Computer Science, and the University of Michigan College of Engineering. Of course, I am also grateful for the references that were provided during this study, and they provided much information. And finally, I'd like to thank you for listening.